Morning, HVAC team. So today we are starting chapter 8, which is types of energy and their properties. The objectives are explain the difference between potential and kinetic energy, list common forms of energy and the units used to measure them, explain how the structure of molecules and atoms affects chemical and electrical energy, explain the relationship among energy, work, and power, calculate energy conversions using watts, BTUs, foot-pounds, and joules, and diagram the electrical distribution system. So at its most fundamental level, heat and air conditioning is about controlling energy. Many tasks performed by air conditioning technicians involve controlling and measuring energy. Understanding energy and how it affects our world is crucial to understanding heating, air conditioning, and refrigeration. Energy, work, and power. Energy acts on matter to perform work. Work is done when energy is transferred to an object. So kind of like how electrical energy is used to power a motor, and the motor turning is the actual work being done. Forms of energy. Chemical. Chemical energy is the energy change that takes place when the atom of materials rearrange themselves to form entirely new materials from the same atoms. It is important to remember that no matter or energy is lost, it just changes. A battery would be a good example of chemical energy. Forms of energy. Thermal energy, heat and radiant energy. Heat is the form of energy that gives molecules their motion. Temperature increase or decrease as molecular motion increase or decrease. Radiant energy is electromagnetic energy that travels in waves. Heat, light, radio waves, and X-rays are examples of radiant energy. Electrical energy. Electricity is the flow of electrons. With electricity, an electron moving from one atom to another creates an imbalance in that atom, which causes it to react or to reject an electron. This electron then has a similar effect on a neighboring atom. This chain reaction carries through the wire to provide an electrical current. Magnetic energy. Magnetic energy is created by the alignment of electrical charges. This alignment gives the entire object a polarity and sets up an invisible magnetic field. This relationship between magnetic fields and electrical flow is the foundation of electrical generators and motors. Let me grab my contactor really quick. Take this away for a quick second. One of my favorite ways to talk about magnetism is the contactor, because once this contactor coil, so the coil is down here, and once that coil is energized, when the wires connected to these terminals on both sides are what's connected to that coil. When these wires have current flowing through them, this coil generates an electric field, a magnetic field. That magnetic field is what pulls the contacts down and closes them. So that's magnetic energy. This is one of my favorite ways to describe how that works, but then there's also the motors use magnetic energy to actually turn, and it's all from the current to the coil. Okay, so getting back to it. Non-renewable, so sources of energy, non-renewable. Non-renewable energy sources have a limited supply. Currently, most of the world's energy is supplied by non-renewable energy sources. Oil, natural gas, coal, or uranium are examples of non-renewable energy sources. Renewable energy sources. So renewable energy sources can be replenished. Interest in renewable energy sources is increasing as researchers look for long-term solutions to the world's energy appetite. Some of the renewable energy sources that have been explored include solar, wind, hydro, ocean, and geothermal, and biomass. Solar probably the most popular at the moment. Energy conversion. Energy can be converted from one form to another. So again, you can't destroy or create it, you can just change its form. So the purpose of an electrical power plant is to convert existing forms of potential energy, such as coal or natural gas, into electrical energy. Energy distribution. Most of the energy we use is produced in a central location and distributed throughout the country. The two forms of energy used most in heating and cooling are electricity and natural gas. So most of the AC systems are going to be one of two types. You have your heat pumps, which gives you your cooling and your heating from the compressor. And then you have what's a little bit more common. I don't know, I guess it just depends on the application. They're both pretty common, but the other way is, the other type of systems are called gas electric systems, where you get your cooling from the compressor, but you get your heat from the natural gas furnace. So those are two different kind of ways. So when you're dealing with the gas electric systems, you're gonna have to have a good understanding of the, thermodynamics and the natural gas furnace, as well as electricity. Energy distribution, electrical. So the laws of physics work against distributing large amounts of electrical power over long distances. Power lines have resistance. The longer the wire is, the higher its electrical resistance. To reduce the loss through the line, it is necessary to reduce the current traveling through it. Alternating current is used for our power distribution because it's much easier and cheaper to accomplish the required voltage changes. The voltage is changed or transformed through a device called a transformer. So the transformers we talked about in Mod 130, transformers in a split system or in an air conditioning system are usually step down transformers. So our power source to our unit is going to be usually like 120 volts for your indoor unit, your furnace, and then like 240 for your condenser to operate your compressor, condenser fan, and all that. So, so going back to the indoor unit, you have, really with both. So you got your high voltage, and then you have your control voltage. Now your control voltage doesn't require as much voltage as your line voltage or your operating voltage. Basically, it takes more voltage to turn your motors and distribute the air than it does to open and close switches. So your control voltage, all that's doing is opening and closing switches, telling the AC to come on, or telling the heat to come on, or telling the fan to come on, or telling the fan to switch speeds, whichever the case. So you have your control voltage doing that stuff, and you still have your operating voltage, which is your high voltage. So your transformer comes into play because the high voltage is supplied from the main breaker from the home. Your low voltage is going to be supplied from your transformer. So you got your 120 volts coming in through the wall outlet that the furnace is plugged into, and then that same 120 volts is going into your transformer. And so that 120 is operating all your motors and stuff. But then that same 120 is going into your transformer, and coming out, because it's a step down transformer, so it's coming out in 24 volts. And that 24 volts is what operates all your controls, opens and closes all your switches and tells things to come on, sends signals to and from the thermostat and to your also to the contactor outside. So at your condenser, you'll have a contactor like this one in your condenser. You got your high voltage that's traveling through here. You got 240 volts resting here, waiting to pass through and power up your compressor and condenser fan. But this 240 volts can't pass until this is closed. When it's open, the circuit is broken. It's open. Once this closes, now that 240 can travel through here and go and power up your condenser. And again, what opens and closes that is your 24 volt control voltage to your contactor coil, which is coming from your thermostat. Switch thermostat to cool, it's going to send 24 volts to your Y circuit, which is going to go to the coil here, close that, boom, now your condenser is on and your AC is operating. So anyway, so you'll have both, and that's where the transformers come into play. You'll have high voltage and low voltage, so you'll need your transformer to give you your low voltage. Energy distribution, natural gas. Natural gas is collected, refined, and distributed through a nationwide network of pipelines. While large gas consumers like electric utilities and industrial plants may get their gas directly from the main pipeline, most users rely on local distribution networks. Standard and SI units of work. Mechanical work. Mechanical work is measured by the weight of an object and how far the object is moved. In traditional English units, this is referred to as foot-pounds. Mechanical force in SI system is measured in Newton meters. This is the force of 1 N times the distance of 1 M, or 1 Newton times the distance of 1 meter. Thermal work. Temperature is a comparative measurement. It compares the concentration or level of heat against known standards. Thermal work is measured in British thermal units, or BTUs, or calories, or joules. A BTU is the amount of heat required to raise 1 pound of water 1 degree Fahrenheit. Electrical work. Since the amps is a rate, or since the ampere is a rate and not a quantity, the watt is also a rate. To measure the quantity of electrical work, it is necessary to state how long work is being done at the rate of 1 watt. The watt hour is the amount of electrical work done at the rate of 1 watt for 1 hour. Watt hours is the product of watts, and hours. Joules, SI unit of energy. Joules are a heat equivalent for mechanical energy. Joules are used today in the SI system for all forms of energy. 1 joule is the work. 1 joule is the work done by a force of 1 Newton moving an object 1 meter. Consuming electrical power at the rate of 1 watt for 1 second is the electrical equivalent of 1 joule. Mechanical power. Horsepower is the rate of doing mechanical work. 1 horsepower is defined as producing 33,000 foot-pounds of mechanical work in 1 minute. Watts, SI unit of power. Although the watt was originally conceived as a unit of electrical power, it is used today as the standard SI unit of power for all types of power. The watt is a rate of power equal to 1 joule of energy per second. Energy efficiency measurements. The EER, or the energy efficiency ratio, is the number of cooling BTUs per hour that a unit produces for every watt of electricity used. EER is determined by dividing a unit's cooling capacity in BTUs per hour by the energy used in watts. So you'd need a watt meter to figure out the EER of like a furnace. So in summary, heating, air conditioning, and refrigeration are about controlling energy. There are many forms of energy, including chemical, thermal, radiant, electrical, magnetic, and mechanical. Energy can be converted from one form to another, but it cannot be created or destroyed. Energy is the ability to do work. Work is the amount of energy transferred. Power is the rate of energy transferred. And the difference between work and power is that work is a quantity while power is a rate. So that is all for chapter 8. I hope that was helpful. Definitely read the book. I say it every day, read the book front to back, read chapter 8, because it breaks down some of the conversions in a little bit more detail. And also just in general, there'll be a little bit more detail in the book. So definitely read the chapter. Chapter 8 is on FlexiQuiz already. So you can go ahead and get started on your review questions. And other than that, stay safe, stay in the house, stay healthy. I will definitely be making the announcement when we can go back to school as soon as possible, because I'm ready to get back in there just as much as you guys. So hopefully that'll be sooner than later. So until then, see y'all on the next one.